Hello. My name is Dr. Linville. This is a lecture on trace evidence part 2 as part of JS 110, Introduction to Forensic Science. Excuse me. This lecture is being recorded in the summer of 2017, June 26th, something like that, to be specific. So if I mention anything in this lecture that's specific to the summer of 2017, quizzes, exams, assignments, the heat, or the end of the rain, you can ignore all that information if you're accessing this archive lecture in future semesters, but all the other material should apply to everyone who's seen this. Okay, so if you're watching these in order, then what has just happened is we've talked about trace evidence part 1, and trace evidence part 1 is a little bit more about using the microscope and collecting trace evidence and different strategies of how trace evidence is useful, sort of going over the linking people, places, and things, the Locard exchange principle. And then also talking about, I think, mentioning that a lot of trace evidence consists of class characteristics. And for most of trace evidence, there's really not individual characteristics. So if you're in the summer of 2017, we've just come off a mock case quiz, which some of you, had trouble with. It happens every semester, and it will send me an email. And with trace evidence, and with all these mock cases, I sort of describe a case, describe the analysis of evidence, and then you're left with 4 different conclusions. With trace evidence, just understand for a lot of these conclusions, it's going to be in the maybe pile, because since we're comparing class characteristics, for example, glass, it's not like there's just one type of glass in a person's windshield. There's a lot of windshields with the same type of glass. For hair, there's a lot of people that have that same type of hair. For fibers, even if you get down to, as is going to be the case with this week's assignment, which I'll mention later in the lecture, even if you get the specific fiber, it's still where there may be other items that also contain that fiber. So it's where there's a lot of class characteristics, and your conclusion is almost sort of a maybe, because other things may also have these traits. Now, if it seems ridiculous where you would do forensic analysis and always get a maybe answer, remember that can be very important, because what you're not doing is eliminating, and a lot of times trace evidence will allow you to eliminate a potential source as having contribute to the sample. Not to mention, if you put this trace evidence along with a lot of other evidence to build your case, it can become pretty powerful stuff as far as convincing a jury of guilt or innocence. Okay, so we're going to start off with hair. You're going to notice a common entry slide here where we're going to talk about the traits of hair or glass or whatever the trace evidence is, how it's used as evidence, and then briefly how you collect and analyze it. All right, so the traits of hair, I mean, if we think about hair, some things that come right off the top of your head are the length of hair, the color of hair. A lot of people will say the curliness of hair, although that can be difficult to measure. You can sort of classify hair as either straight or curly, and that can be artificially changed. If you look at hair under a microscope, though, then you start to pick up some additional features. Like we're going to see that if you use a compound microscope and look through the hair, it looks sort of like a pencil, and you're going to see a cortex, a medulla, and a cortex, a medulla, and a cuticle. And the medulla will either be there or not be there, and if it is there, it has some unique shapes to it. So with hair, you can look at it both just macroscopically, just with the naked eye, and you can also look at it with a microscope, but you're just sort of compiling a list of these traits. And again, they're all class characteristics, so even if the evidence matches every class characteristic of your known sample or your suspect's hair, to put it simply, then you can't say that the hair definitely came from the suspect. The greatest conclusion that you can make, or strongest conclusion that you can make, is a maybe. All right, so hair is just a fiber of animal origin. So from a forensic science perspective, we're not really differentiating hair and fur. It's the same thing. It is a thin thing that grows out of animals, I guess. Hair is usually growing, This is going to become important later on. It's important to understand that hair goes through a cycle, and not everybody can just grow their hair out until it's past their feet and, like, dragging behind them, because after a certain period of time, and we can sort of see this, with body hair, it's the cycle is a lot shorter and it falls out a lot quicker. It doesn't grow quite as long, whereas with head hair, it grows a little bit longer until the head hair falls out. Therefore, you can grow it a little bit longer. But I always give the disgusting example of looking, when I change the sheets on my bed. When I was younger and didn't have a wife to do that for me, maybe I would go a week or 2 or 3 or 4 or longer without changing my sheet. And when I change them, there's like all this hair in the bed, and it's like I was a disgusting human being. Why am I just shedding all of this hair like a dog? But it just, that's naturally what happens to body hair and to head hair. It sort of grows and then falls out, and then a new hair replaces it, hopefully. So what does that mean? It means hair is constantly being shed, and it would not be unusual to find hair from a person at a crime scene, be it primary crime scene, secondary crime scene, or on a person's clothing, as with pets, et cetera, et cetera. The other thing is, when it comes to DNA analysis for hair, if you just have a cut hair, meaning that you have the hair shaft, it's cut with scissors, so you have what looks like a hair, it's possible to do mitochondrial DNA analysis. We talked about that in the DNA lecture. It doesn't give you as good of information as nuclear DNA or STRs. But the good thing with hair is so it's important to understand that hair is not composed all of cells, okay? But the root of the hair is the living portion of the hair, and the root does have cells and therefore nuclei and chromosomes and DNA and short tandem repeats in it. So what does this mean? The rule of thumb is, if it's a cut hair, you might not be able to get an STR profile out of it, but if it's a hair that's been pulled out, forcibly removed, Dr. Linville, when is that going to happen? Well, if you think about it, in a violent struggle, it may be where the victim grabs the hair of the attacker and pulls out hair, so therefore in the victim's hand, you may find hair that has a root attached that you can target for DNA analysis. Okay, so that's sort of an aside of using hair as evidence. If you can do DNA analysis on hair, then you do DNA analysis. The type of microscopic analysis we're going to talk about is if DNA has failed, or if maybe you're just dealing with animal hair for some reason and want to get some additional information from that. Okay, so hairs are shed from people. They can link a person to a crime scene. This slide just reminds you that it's not just human hair that is involved in crimes, although it can be, but it's also animal fur. Not because animals commit crime, but if you imagine, if somebody were to break into my apartment and steal my television and for some reason roll around on the floor, they're going to be covered in cat hair because we got 2 cats. It's summer. There's cat hair all over the place. Okay, so if a forensic scientist did the analysis on that hair and found that the traits of that hair were similar to the 2 cats that live in my apartment, then it may be possible to link that person to this crime scene through animal hair. Okay, so let's say that that we do have either a victim with hair, grasped in their hand, or we have a burglary suspect with a bunch of animal hair on their pants. How are we going to collect this hair? There's several different ways to do it. To go back to the collection methods we talked about, if it's hair in a hand and you see big pieces, then you just collect it with forceps and you collect what you want. But hair is one of those items that may be found over a large area, a piece of clothing, and it may be mixed in with other things that aren't as important to the investigation. So tape lift comes in handy for collecting hair over a large area. Okay, and whether it's, with forceps individual hairs or with a tape lift, you're going to, flip the tape off onto itself to sticky end, and then probably stick that in a paper envelope. With forceps, you probably want to stick the hair in a plastic envelope or something without holes in it to make sure that it doesn't fall out of the envelope. Okay, so when we get the hair back to the lab, we can measure the length and the color and the curliness just with the naked eye. But then when we throw hair under the microscope, it's going to look something like this. And again, we're using a compound microscope. We're shining light through the hair, and we're sort of looking at the inside of the hair. And we're going to see that in some cases, it's not always going to look like this, but the way I want you to think of it is like a pencil as far in regards to the three different portions of the hair. Okay, so we have the cuticle, which we'll talk about in a couple slides from now, which is the outside of the hair. It's sort of like the paint on the pencil. Okay, and in hair, the cuticle is actually scaly, sort of like scales like a snake. There's also the cortex of the hair, which is sort of like the wood of the pencil. It makes up a majority of the inside of the hair. It contains pigment blotches and affects and causes the color of the hair. And then we also have the medulla, which is a type of feature, if that's the right word, that may or may not run down the center of the hair. And if it does run down the center of the hair, it may have different shapes. So the medulla is sort of like the lead of the pencil. Okay, got that cuticle paint, cortex wood, medulla lead. Okay, so if you look at, and this is not an example of what I'm going to talk about, but let's say you look at 3 brown hairs. Okay, it may be possible once you get them into the with the naked eye, they all look like brown hairs. When you get them under the microscope, it may be where you'll find that some brown hair has a fragmented medulla, like over here, so it's sort of like dashed. Some brown hair may have an absent medulla or no medulla at all, and some brown hairs may have a very thick medulla down the center. Now, sometimes this dark color of the medulla is caused more by air pocket, what can be confusing is you may see light hair that has a dark medulla. All right, so don't think dark medulla means dark hair. That's not necessarily the case. But the medulla may be fragmented, absent, or present, as it says there in the last bullet. Okay, now species ID or human ID. We're going to see this in several different slides, so I want to explain what I mean by this. The medulla can be used to help differentiate species, meaning you can look at the medulla and draw a general conclusion about, is this human, animal, what type of animal. Now, unfortunately for the human type medulla, which is called amorphous, I don't think we're going to get into the details of the medullas, but an amorphous medulla, let me go to the next slide and see. No, we don't get into that at all. Excuse me. It's the scales that I have the animals for. I'm confusing my slides. An amorphous medulla, which looks like what you're looking at there, sort of the solid dark blob, that's not just found in humans. That can also be found, I think, like sometimes cats and dogs have similar amorphous medullas. But like a rodent's medulla or squirrel medulla, it sort of looks like a bunch of clear beads stacked on top of one another. So by looking at the medulla, you may be able to say, oh, this is definitely not a human hair, or this is a human hair, or, oh, I think this is a type of, rodent. This medulla is consistent with a horse or deer. So just sort of general categories of species you can put a hair into. When I say human ID, that doesn't mean that you can identify it as human. It means you can differentiate humans. So in other words, Annette and I may have the same color of hair. Well, hopefully not. Maybe if I was younger, then I've oh, wait, some of you can't see the webcam. So I have gray hair, which is a recent phenomenon. I had an argument about with my students a couple semesters back about what color of hair I had because I was convinced I had brown hair, and it turns out that that's not the case. Anyhow, but let's pretend, hey, who knows, maybe Annette has gray hair as well. All right, so we could have the same color of hair, but our medulla may look different. So that means that medulla, for human identification, it can differentiate humans. Different humans may have the same color of hair, but their medullas may look different. All right, cortex features. So this is the color of the hair, all right, and this can be used to differentiate humans. Usually looking at the cortex won't tell you much about the species because all species, like the cortex sort of looks very similar where it has splotches in it and it's just sort of a general shaded color. The one thing that you can use for not necessarily species ID, but to tell whether it's human or non-human, is in some animals, like I think raccoons are one example, the color of the hair naturally varies at the root middle tip. So you may have at the root, it's like a white hair, and then in the middle, it sort of gets a little bit darker. Then at the end, it gets a very dark black. In humans, the hair is the same color the entire length, unless it's been dyed artificially. But if you see this natural color variation within the hair, then that indicates it's an animal hair and not a human hair. So that can be one thing that the cortex may be helpful to forensic scientists. All right. The cuticle are the scales on the outside of the hair. So notice that this is species ID only and not human ID. In other words, you can't differentiate humans by looking at the cuticle because all humans have the same cuticle shape. Okay, and it's called imbricate. And we can see there it's just a scale pattern that looks very similar to like a snakeskin scale pattern. All right, the coronal, the spinous, there's some other cuticle shapes, the scales on the outside that may indicate whether it's a rodent or a cat or, well, I think cats are sometimes imbricate as well. But the cuticle shape may give the forensic scientist an idea of what species of hair it is. Okay, so if you are collecting, a bunch of hair from the trunk of the suspect's car and you're trying to weed out what's human hair because you're trying to find a match to a victim, human victim, and what's animal hair, you may be able to do this with the cuticle. Now, the cuticle, if you'll notice in the previous slides that we're looking at, the cuticle can't really be observed in a compound microscope. Okay, you just sort of see the inside of the pencil. So how do you observe the pattern of the cuticle? It's an indirect process where you make a cast of the hair, and or you make an impression of the hair. I guess you never really make a cast of it. So you'll just use clear nail polish and you'll smear this on a microscope slide, a glass slide, and then you'll lay the hair in the clear nail polish and allow the nail polish to harden. After it hardens, 5 minutes, does that sound right to everybody? Then you rip the hair out, and what's left in the nail polish is the impression of the outside of the hair. You throw that underneath the compound microscope, you can take a very close look at it, and it gives you an indication of what the cuticle pattern is. Okay, again, imbricate, it says, well, maybe human, maybe a couple other species of animals, but if you find one of those strange ones, then that can indicate that it's definitely not human. Okay, so you put all those characteristics together, and, what can you say? You get on the stand and you say, well, the hair that we found at the crime scene or the hair that we found on the victim or whatever is consistent with the hair of the suspect. And you name all the traits that you compared, and then the forensic scientist has to give the jury some type of indication of how rare that hair type is or how common that hair type is. And you can imagine, I mean, for a person with brown hair, your hair is probably going to look very similar to a lot of people. It's not as though there's a lot of unique characteristics in hair. But that's the case with trace evidence. Okay, fibers. We can have a little bit more variation with fibers than with hair. I mean, hair is a type of fiber. So here we're going to mention hair within our fiber discussion, but then also talk about other types of fibers as well. Fibers are typically a small, thin rod type shape item that can be spun together to form thread, and then the thread can be woven together to form rope or fabric. And so fibers can be shed from that clothing or rope and found at a crime scene, and they can be compared to the item of clothing or the rope that they came from to try to determine whether they have a common origin. All right, so fibers, we have a lot of class characteristics. Again, fibers, we don't really have any individual characteristics. If you're watching this in the summer of 2017 or in future semesters, it is during this section, the fiber section, that I'm going to give you very strong hints and advice on how to complete the assignment for this week. Okay, so it may be a good idea to pay attention. All right, the reason why fibers are good or as far as being used for evidence is that they're easily transferred from clothing or a rug or carpet from one item to another, from one person to another, or from the crime scene to a person, or in the case of clothing, the person to a crime scene. Okay, so they're very easily transferred from people, places, and things. Also, when it says significant persistence, fibers tend to get trapped in other fabrics. So in other words, if somebody comes in here and murders me, all right, and I'm wearing these clothes that I'm wearing, and they throw me in a trunk of their car, okay, that has sort of loose carpet in it, or really any carpet in cars is pretty cheap, all right, and then they dump my body in the woods. What's going to happen is when they take my body out and they're carrying it through the woods to find, I guess, a good location, I'm going to come out of the trunk and I'm going to have a lot of fibers on my clothing. Okay, some of them are going to fall off relatively quickly because they're not really stuck on my body. But for those fibers that are stuck, like woven in between the fabric of my clothing or in the cuff of a pant leg or somehow gets in my pocket or something like that, they tend to stick around. Also, they don't naturally degrade. It's not like blood or body tissue or anything like that. So it's possible where if a body is recovered, even maybe months or years, maybe a short number of years after the body's been buried, depending on especially if it's a synthetic fiber, the clothing and those fibers may still be able to be recovered from the gravesite or recovered from the body. So they last for a long time. That makes them a valuable piece of evidence in some circumstances. Okay, so at this part of the lecture, we start talking about just general categories of fibers. So this is to understand a little bit more about the wide variety of fibers that a forensic scientist may be looking at. Also, these slides are good for multiple choice questions, like if I ask you which of the following is an example of a natural fiber, then you should be able to, pick out an example. Manufactured and synthetic fibers are very similar. They're slightly different, so pay attention to the difference there. Okay, natural fibers, there's a variety of natural fibers, one of which we already talked about, hair, so it's a subcategory, or hair is a subcategory of fibers. But wool is also like a type of animal hair. Cotton is plants can be types of fibers, so hemp is also a plant. We're also going to see there are some minerals that are considered fibers, but anything found in nature is a natural fiber. So don't be confused, if it's dyed or treated in any way, that doesn't matter, okay? It's still a natural fiber. All right. Okay, so we're going to have three categories of natural fibers. The first is going to be animal fibers. Now, animal fibers, you may think, wait, didn't we talk about this with hair analysis? Well, yeah, and you would do a very similar analysis on wool or, well, not really silk, but any type of animal hair that you collect. But the difference is where they're found. Like with the previous hair analysis, we're thinking more ripped out of a victim's head or pet hair that's been transferred. For animal fibers, these are fibers that are used to make clothing, like used to make fabric or rope. And we're going to see here that what we're going to go over several times is if you take a short fiber or a short hair, you can spin those together to form a thread. And then that thread can be spun together to form a thicker thread or woven together to form fabric. So for wool, the hairs from sheep, I just want you to understand it's not like in the cartoon where if you pull a hair from a sheep, it starts spinning around and it's just one long hair that's attached to the sheep. No, they're longer. You can tell because they're woolly. They're very, thick. So it's longer than maybe the hair from you or I. But it's still where those hairs are then spun together to form thread, which can be spun together to form yarn and then used to make a sweater, let's say. Now, if I'm wearing a wool sweater, what's going to happen is even though that thread is woven together to form fabric, it still may be where some of those hairs sort of unravel from the fabric, unravel from the thread they were twisted into. And if you rub like your hand across a wool sweater, you may be able to get it to shed some of those hairs. Not necessarily easily, but it's definitely possible. Okay, silk is the same thing. Silk, Uh, well, excuse me, silk is not the same thing. Silk is a little bit different in that silk is in a filament form. And we're going to talk about the difference between filaments and staples. But whereas hairs are spun together to form thread, silk, you can almost think of it as fishing line. It doesn't have to be spun together. It's just this string of silk that comes out of the silkworm uh, is a thread. It can be very long. So that can be taken and it can be woven together to form fabrics. And silk tends to feel very shiny and it doesn't really shed. It's not soft like, animal hair that's sort of fluffy and if you rub it, some hairs may come off. Silk tends to not shed. All right. So it's not going to necessarily be found in fiber form on a body, but if you're dealing with any silk fabric or something, and again, the point of this discussion is just give the wide variety of types of fibers that are used in textiles, I guess. Okay, plant fibers, the most common is cotton. So here in Alabama, if you run down to the Cotton Picking Festival in Vincent, is that where it is? I forget where the Cotton Picking Festival is, but it's somewhere close. You can throw your child into a large bin of cotton or maybe jump around there yourself. But there's cotton fields not very far, so maybe in this region it's more common to have seen cotton come off of the plant or see a cotton plant. And you'll see that it's short hairs. They sort of look like hairs, although not quite like animal hairs. I mean it's cotton, but they're short hairs that are then spun together to form thread, and then that thread can be spun together to form thicker thread or woven together to form fabrics. So they are seed hairs, I guess is the name for them. Okay. Now, the thing with cotton to recognize is since it's the most common, it's not very useful for forensic scientists. Like if I find a dead body and it has cotton fibers on it, well, especially if it's white cotton fibers, that they're all over the place. That could have come from anywhere. All right. So sometimes cotton fibers, even though they're found in a lot of places, might not be as useful in a forensic science context. Okay, some other plant fibers. We have linen, which is a stem fiber. Kapok is a seed hair that is similar to cotton. I think kapok, if I'm not mistaken, has a lot of air pockets in the seed hair, and it's used as stuffing for some materials like life vests, life preservers, stuff like that. But this just sort of gives you, linen, stem fiber. If you've ever taken a stem of a plant and open it up, well, it has, I guess, of a linen plant or a similar plant. Some stems are very fibrous in there where it comes out about the length of a hair, and again, they can be spun together to form thread, which can be woven together to form fabrics. So there's a wide variety of different plants that tend to be, not all the time, but can be a little bit rougher if it's the stem fiber. So we think of the, thicker, rougher rope that's used in gardening, or like the tablecloths. What are those brown tablecloths called? Annette, can you help me out? Somebody? Well, you're at home and you're saying, "Oh, Dr. Linville's an idiot." Of course. Burlap sacks. That's what I was thinking of. Burlap table. Well, I don't know why I'm thinking of burlap tablecloths. I think I've been watching Home and Garden Network a little bit too much. Anyhow, wide variety of plant fibers. Mineral fibers, asbestos is an example of a mineral fiber, which isn't used that much anymore, because it kills children. But it's important to understand that in the context of forensic science, we still refer to something as a fiber, and it may be, not traditional plant or animal. It may be a fiber that is used to fill something. Maybe a mineral fibers is, and the most common was used to fill old versions of drywall. And that's why if you have a very old building that has, or excuse me, not drywall, asbestos was used as insulation. So if you have a very old building that had asbestos insulation and you start tearing down that building, then it releases these asbestos fibers into the air, which are very dangerous. Now, it says there in the last bullet, which I think is kind of interesting because you know, a lot of things that cause cancer, you think it's like a toxic chemical, a carcinogenic chemical, and that's a reason why it causes cancer. Asbestos, the mechanism is a little bit different. It's really the shape and the size of the fibers that causes so much trouble. And with most, you know, we breathe in dust all the time. If you ever see like light come through a window, you see all the dust floating in the air and it grosses you out because you're thinking, oh my God, I can't believe I'm breathing all that into my body. But if you get dust in your nose or lungs, you have a system for sort of washing it out the dust, and then you swallow it, and it goes, you know, into your stomach and disappears. Uh, so for very small particles, our body has a way of cleaning it out. For large particles like golf balls, well, you can't really breathe in a golf ball. You can choke on it, but you can't breathe in it. So that golf balls aren't going to get on our lungs. They're too big. But if you have this like sort of in between, you know, in between dust and a golf ball, okay. But if you have these mineral fibers, it's not just the size, but it's the shape. They're small enough where they can be breathed in. But because they're such thin rods, they sort of get into your lungs through the air, but then they get wedged in there and they get stuck. And when they get stuck, they cause irritation, and your body reacts to them, and it reacts to it in the wrong way. And this can lead to inflammation and eventually lead to cancer in the lungs. And so that's why asbestos is bad, and you shouldn't breathe it in because it gets stuck in your lungs and causes cancer and kills you. Okay, I've been hinting at this when I talked about silk and talked about, you know, spinning together hairs. Here, the general terms for the way that thread can be formed are a filament or a staple. So all hairs are sort of considered staples. All right, seed hairs, even stem fibers, you know, like linen would be staples, where in the bottom there, they're shorter than the length of the thread. All right, and so the individual hairs, the individual staples are shorter than the length of the thread, and they're just sort of overlapped with one another, as we can see down here, and then spun, twisted together, and then they form a very long thread that can be as long as you want it. Okay, so it's a way of taking these, you know, short hairs, spinning them together to form a long thread. A filament is a long continuous fiber, sort of like a fishing line, if you think of it like a fishing line, where it can be as long as you want, well, within reason. For silk, there are some natural, you know, limitations, but it can be extremely long, like fishing line, and you can use that as your thread, and then you can weave that together to form fabrics. And the difference from a forensic science perspective is if you have fabric that is threads that are forms of staples that are woven together, then it's possible like one of these staples or more can be shed and left and transferred to a person, place, or thing. For the fibers like silk, it's not possible that just like one little fiber will come loose from the fabric and, you know, be shed, or it's a lot less likely. So when it comes to transfer, staples are a lot more useful than filaments, I guess. Okay. Also, they give the clothing or the text or whatever it is different textures as well. I mean, the filaments tend to be more shiny and nylon-y, like rain jacket type of stuff, or silky smooth, whereas anything spun together with staples, you know, hair spun together, tend to be a little bit softer. Okay, so we went over natural fibers. Now we're going to go over manufactured fibers. Manufactured fibers and synthetic fibers are very similar. Manufactured fibers, another name is regenerated fibers, but I think I used manufactured fibers on the Quizzer exam. It's where you start with a natural material, cellulose, plant material, and then you dissolve it and re-solidify it in a controlled fashion where you're forming this, I guess, unnatural fiber. Now, what I want you to think of manufactured fibers and synthetic fibers, how you can visualize this, and this is a terrible example, okay, but again, it's for visualization purposes. I want you to visualize it as sort of where if you have like this big vat of liquid and you poke a hole in the bottom and the liquid starts coming out of that hole, and then as the liquid comes out of that hole it sort of, hardens and solidifies. Okay, it's sort of where you have this vat of chemicals and then you can shoot it out, in whatever shape or size or thickness that you want. Also, when it's coming out of that hole and solidifying, you can keep it in filament form, like a fishing line, just sort of let it pile up, solidify and pile up. Or you can cut it as it's coming out and solidifying, and then it would be in staple form. Okay, so something like rayon is a good example. Sometimes rayon comes in filament form, and it feels more silky. Okay, it's sort of like a fake silk type material. But if you cut rayon into staple form and then twist those staples to form threads, it's much softer, and in that sense, rayon can mimic cotton a little bit more closely. Okay, so it's sort of where for these manufactured synthetic fibers, you can play around with them and try to mimic natural fibers. You can mimic silk, you can mimic cotton if you want. All right, synthetic fibers don't start from a natural material, don't start from cellulose. So it's like you mix up a big vat of chemicals, poke a hole in the bottom, it comes out and it solidifies. So just like manufactured fibers, you can let it pile up like a fishing line in a long filament, or you can chop it up into staples and then spin those staples together to form a softer thread. So therefore, for synthetic fibers, we can have more of the silky, smooth rain jacket material like nylon. We typically think of that. With polyester, we think of polyester as sort of like a fake cotton. It's a little bit more softer, although it tends to ball up in those little polyester. But anyhow, acrylic, you can sort of cut it to mimic wool, and acrylic sweaters sometimes feel like wool sweaters. For acrylic and polyester, probably more acrylic, since it mimics wool with that looser thread. Acrylic sweaters tend to shed their fibers a little bit more easily than maybe polyester or nylon. So you can imagine if you're wearing like, this fluffy blue sweater and you start hugging your victim to death, okay, death by hugging, then after you stop hugging your victim, they're probably going to have some of those blue fibers from your sweater on them. Okay, so way to go, Freddy Krueger, you just got caught. Maybe throw away your sweater, not wear the same one every time you're entering somebody's dreams. I got a little off track here. Okay, so for fiber analysis, okay, you collect your evidence sample from wherever, okay? If you remember our Tom Bosley situation, Tom Bosley's body is found in a dumpster. We collect fibers, and we want to try to match those evidence fibers from the crime scene to a location from which we think it came. Okay, in this case, it was Scott Baio's truck or van. Now, the case that you guys are going to be testifying on, or your assignment for this week, is very similar, where you find fibers on a body, and you have to testify about their source. All right. So you're going to compare class characteristics, and I think we're going to have the conclusion. So you look at them under the microscope. You can look at them with the naked eye. You start to compile things like color, shape, width, refractive index, and I think we're going to look at a couple other things as well here. But what I want to say about your assignment, and maybe this is later in a conclusion slide or something, is you're going to compare all these class characteristics, and even if they match, which hopefully if you're going to court they do match, you remember you can't say that the fibers definitely came from the suspect's car. Okay, so how do you testify if you can't say, get on the stand and say what the jury wants you to say? Yes, these fibers came from the suspect's car. What you have to do is you have to let the jury come to the conclusion about the likelihood that it comes from the suspect's car. And I'm going to, so number one thing is don't say, yeah, it definitely came from the suspect's car. The other thing about this assignment is I try to trick you by asking the following question. What is the likelihood that the fibers found on the body came from the trunk of the suspect's car? Okay. Now, the reason this is a trick question is because likelihood has to do not only with the scientific analysis and the class characteristics, but it also has to do with motive, alibi, and a lot of other things. For example, we may find that that there are fibers on a dead body that match the fibers in the trunk of my car, right? Okay, so the analysis doesn't change. Okay, the analysis of the unknown samples matches the fibers on the trunk of my car, and I think in the example you even weed it down to exactly what type of fiber it is. Okay, but the reason why you can't testify on likelihood is because just in that situation, is it likely that the dead body was in the trunk of my car if all the class characteristics match, or is it unlikely that the fibers came from the trunk of my car? What do you guys think? You can sort of answer yourself, and then if you want to throw it in the chat box, you can. Okay, if there's a body found in the woods and fibers are pulled off of it and all the class characteristics match the trunk of my car, is it likely or unlikely? A lot of people say likely, because it's a match. And a lot of people will say unlikely because there's a lot of other cars, other Saturn ions, well, not so much anymore, out there driving around with the same carpet. And you're sort of both right as far as the matches suggest the body was in the car, and the fact that there are other cars suggests that it might not be my car. But the reason why the likelihood can't be mentioned in your testimony is because let's say that the body was my ex-girlfriend that somebody saw me arguing with the night before the murder. Okay, now it's likely that it came from the trunk of my car, right? What if the body was one found in Seattle, Washington? Okay, again, the scientific analysis is the same. These fibers are consistent with Dr. Linville's car, but now it's very unlikely that that body was in the trunk of my car. And you, as the forensic scientist, you don't testify about any of that stuff. You don't testify about whether there was an argument. So in other words, I'll take off points if you mention the argument, okay, that's described in the situation. It's where you just have to give the jury information that you have, and that is you need to describe what you did to the fibers, what type of analysis you did, and what conclusions you came from. Don't assume that they know what you did, that you compared the color and the refractive index, et cetera, et cetera. You need to tell them that's what you did and that it matched, okay? And then you need to give the jury an indication of the likelihood of that match. And how you do that is, okay, how many other cars have that same fiber? Okay, so that's sort of where the beginning and end. You just tell them what you did, tell them what other cars have it, try to be as accurate as possible. Don't just say, other cars have it. No, be specific if you have that specific information. All right, and then the jury, along with all the other evidence, put together to figure out if they think that the victim was in fact in the suspect's car. Okay, thus ends my tips for this week's assignment. Hidden in the middle of this lecture. All right, class characteristics. So I mentioned color of and again we're on fibers, size. The cross-section shape can be different for synthetic fibers. And like I described before, we had this big vat of chemicals and you poke a hole in the bottom. If you think of like the Play-Doh Fun Factory, if any of you are still familiar with what a Play-Doh Fun Factory is, my son actually had, it was like a food set or something, and had something similar to the Play-Doh Fun Factory where you shove Play-Doh in this squisher, I don't know what the term for it, and you can slide like different shapes in front of the Play-Doh, and then you squish the Play-Doh and it comes out in different shapes. Well, you can do the same thing when you're making these synthetic fibers, where you can sort of squirt it out into these different shapes, and some of the fibers that have sort of more air in them will be a little bit lighter, maybe good for filling material, et cetera, et cetera. So you can get different characteristics out of your fibers by adjusting their cross-section shape. There's actually I don't think it's Walter Williams. I always get this case, my two cases confused, but if you look up serial killers and carpet fibers, maybe that's going to do it for Google. There's one famous case with the serial killer where these bodies were turning up dead, and they found these unique fibers on a couple of the different bodies. So they started to link the cases together through these fibers. And when they eventually arrested the suspect, they found that these fibers matched the suspect's van, similar to all these examples I've given you, but it was a rare fiber, and it had a very strange cross-section shape. It was like a square with 4 holes in it. And the uniqueness of that cross-section shape was one of the characteristics that allowed them to come to a strong conclusion that this was the person. Okay, so cross-section shape, color. Refractive index is something else that you can look at with fibers, and we're going to talk about this with glass as well. What refractive index, we can read the NERD definition there, the ratio of the speed of light in air or in a vacuum to the speed of light in another medium. What that means is when light hits a fiber or glass, it will slow down while in that glass or fiber, and then when it exits the glass or fiber, it will speed up again as it goes back into the air. So if it comes in at an angle, what will happen is when it hits the fiber, it sort of turns a little bit, all right? And then when it exits, it turns again. So when it enters and exits, it's parallel. It's just a matter of how much it turns while in the glass or in the fiber. All right, so it's sort of like the thickness of the glass or fiber in regards to light passing through it. And this can be measured. It can be assigned a value, you know, like a number value, refractive index. And if you have two fibers that look very similar but they have a different refractive index, you know that they cannot be the same chemical composition. They cannot be from the same origin because that's a characteristic that's different. All right, so refractive index is a class characteristic that can be used. Okay, chemical composition. You can use advanced instrumentation. This is an FTIR. We'll talk about more about this instrument with drugs. But it's where you can take a fiber and squish it in a infrared spectrometer, and you can get the absorbance at different wavelengths of infrared light through it, and different types of materials will absorb differently based on the bonds in the molecule. But what does that mean? It means you can look at something, a picture like this that's from a fiber, and you can come to the conclusion, oh, that's polyester. You can look at something like this and come to the conclusion, oh, that's nylon. Now, these are not the spectra from polyester and nylon, but it just sort of gives you an indication of you can take a fiber, look at it with this advanced instrumentation and get an idea for the type of fibers if it's synthetic. This doesn't really work with hairs, but for synthetic fibers you can narrow it down exactly what it is. Or if it's some, you know, weird trademarked polymer that they've come up with to make fibers, you can also get specific IR spectra for that too. Okay, when it comes to threads or yarn, rope, cordage is the general term. With a lot of rope, what you'll find is if you start untwisting the rope or unbraiding the rope, you'll find a rope is composed of smaller ropes. And then you take those smaller ropes and you start to untwist those, and you'll find that those smaller ropes may even be made of smaller ropes. And you keep working your way backwards until you get to a thread that is either a filament or it's composed of staples, you know, staples spun together to form a thread. So it's sort of like at each level you can count the number of cords that are twisted together, and you can also look at the direction they're twisted, and these become class characteristics. So you could have two thick white ropes that look the same, but when you start to unwind them, you'll find that one rope is composed of 5 smaller ropes and the other rope is composed of 4 smaller ropes. Okay, therefore they can't have the same origin. If one rope was used to tie up the victim and the other rope was found in your suspect's truck, you know, you can say, well, this wasn't the rope used to tie up the victim, okay, because it has different class characteristics. All right. Now, how do you determine the twist? Okay, there's an S twist and a Z twist. And what I want you to look at is the middle of these letters. Okay, so you can see how in an S, the slant is in this direction. Okay, and in a Z, the slant is in this direction. All right, so what you do is you look at a rope and you look at the direction of the slant and then you determine whether it's S or Z. Okay, so the rope's on the left there that I just drew the lines through. Would that be an S twist or a Z twist? We'll pause for you to answer. Yes, and Annette has it correct. So I assume everybody is as sharp as Annette. Everybody said Z, right? Very good. Okay, this, the rope on the right, is that an S twist or a Z twist? Well, it wouldn't be any fun if it was a Z twist, right? Yeah, so that's an S twist. Okay, on a quiz or exam, I may show you a picture, ask you which twist it is. There, now you know how to do it. Okay, this just gives an example of how if you take a bunch of class characteristics, you can make a chart for an unknown fiber and compare it to a bunch of known fibers in order to figure out what the origin is or eliminate a lot of known fibers. All right, so here with all of the K's are different knowns and then we have the unknown at the bottom. You can do this analysis, and again, if one of these class characteristics is different, then you can eliminate that known fiber as being from the same origin as your unknown. So it's just sort of like a matching game, and if you go column by column, and these are just refractive indexes with different polarization of light going through the fiber. Okay, don't worry too much about that. We have melting point, birefringence is another optical measurement. But we get these numerical readings down here. We can see 1.52. Let's see here. No, can't be that. Can't be that. Probably not. Maybe. We won't eliminate that one. Nope. 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 Possible. No. Possible. Okay, so there, just looking at one class characteristic, we've eliminated 7 samples and are left with 3. We go to the second class characteristic, and this one's out. Nope. And this one is still in the running, and this one is nope. Okay, and then we go and we find this one matches, this one matches, this one matches. So our unknown fiber is consistent with K3. It doesn't mean that they're definitely the same. You know, if the unknown is a fiber found on a dead body and K3 are fibers from the trunk of the suspect's car, doesn't mean there's a definite match, but if we were testifying about this, we would just list all the class characteristics that match. Okay? All right. So that's it for fibers. You know, it's very similar to all trace evidence. You just make a list of all the class characteristics you compared and see if they all match, and then try to find the rarity of samples with those class characteristics. All right, so glass. What is glass? How's it involved in? Glass is fused inorganic materials. You know, what is it? Silica dioxide or something like that. It's not crystalline, so sometimes you'll hear some nerd say, well, actually, glass is just not a super cold liquid, but it's some type of liquid, and the window panes will melt if you just do nothing to them for 50 years. And then inevitably somebody would punch me in the face as I'm going on and on about that in the 3rd grade. But with glass, you know, it's sort of this silica dioxide at its base, but then you can mix a lot of different elements in it. You can modify it. You know, Gorilla Glass is obviously a lot more sturdy than the cheap window pane glass that you buy at Home Depot, you know, to fix your grandma's windows every time you hit a baseball through them. I'm sorry, this is, I don't know when this turned into Leave It to Beaver, but, you know, headlight glass is a little bit different from, my favorite is on CSI where they found glass, was it on a dead body or something, and they found out it was boat glass because there was some weird element in it that apparently is only in boat glass. So you can put a lot of different things in glass, make it different colors, textures, shapes, hardness, thickness. So there's a lot of class characteristics. There's a lot of characteristics to look at with glass. Now, with glass, we can use it like hair and fibers, where small fragments may be transferred to people, places, and objects. Okay, I smash a window at a crime scene when I'm burglarizing the house, and a bunch of the glass falls into my pant cuff. Okay, that can be used as trace evidence, just like we've been talking about. But also, glass offers glass can be used to provide information about, in regards to reconstructing the crime scene. And this is most easily visualized if we're talking about gunshots or bullets going through glass. Whenever glass is broken, you can not only tell if it's hit multiple times, you can not only tell which location was hit first, or in the case of bullet holes, which bullet went through the glass first, but you can also tell the direction it was hit. And this may become important to know whether, you know, the glass was hit or bullet entered from the outside or the inside, or if a window was smashed, you know, oh, it turns out it was smashed from the inside after, you know, because they were faking a burglar or something like that. So you can tell the direction that glass was broken or the side of glass that was struck, and also the order of fractures. All right, so for trace evidence, you know, with glass, we're not going to go, you collect it like you do hair and fibers. Pick it up with tweezers, throw it in a plastic envelope so it doesn't slide, you know, slide away. For reconstruction, there's a couple terms I want you to be familiar with. So radial cracks, concentric cracks. If I show you a picture, ask you a multiple choice question, be able to answer correctly here. When an item strikes glass, the radial cracks go out from the center, sort of forming like a bunch of pieces of pizza, and then the concentric cracks sort of like cut off the tips of the pizza, and they can actually, you know, go, or so they form sort of the circles around the center impact. All right, and this sort of shows how the concentric cracks form. It's where if you imagine, you know, a force is going into a piece of glass, it's not just going to bend in one direction. It bends in one direction, and then it also cracks in another direction a little bit farther up the glass. And this can sort of set a wave where you would get a lot of different concentric cracks as well. All right, the direction of the projectile, sometimes when glass is broken, especially with a bullet, you may get what's called coning, where the glass sort of explodes out from the opposite side of the impact. But this coning is not always reliable, because sometimes like a bullet may come from this direction and hit the glass and then bounce off, and it creates sort of like a dent in it that sort of looks like a cone. But what will never lie to you are the conchoidal fractures. And if you take a piece of glass and turn it on its side, okay, so you're looking at the side of the glass. So this is sort of like the front of the glass and or the outside, and this is the inside. So you're taking it out of the pane and looking at the side of it. You'll notice that there are small fractures. These are the conchoidal fractures here that you can see on the side of the glass, and they're always pointing and originating from the side of impact. Okay. So in that sense, you can ignore the cone, and if you see the conchoidal fractures originating from here, you know the bullet entered from this side. All right, and again, I may show you a picture and have you reconstruct, you know, which side did the bullet enter from. All right, the order of the projectiles. This is PowerPoint award-winning art. I created an award and I gave it to myself, so technically, when I say that this is PowerPoint award-winning art, that technically that's correct. Okay. So these represent the radial fractures and conchoidal fractures, albeit very lousily. And what you can see here is with 1, 2, 3, you can actually look at these cracks and be able to tell which one was made first. Okay, and the reason that you can tell is because as the radial cracks go out from the center, if they hit something and stop, then that means another crack was already there. So you can see in this case, 1 was made first, 2 was made second, you know, boom, because this radial crack stops right here. So it means that this radial crack was present before this one. Okay, so 1 was there before 2. Because these radial fractures stop at this crack, it means this crack was there before these, 2 was there before 3. Okay, so it looked like this. Bang, bang, bang. Send your letters to the dean about what a fantastic professor Dr. Linville is. Mention this slide. Okay. For trace analysis, so let's say it's the fragments of glass found in my pant cuff. You're just going to look at the class characteristics, the thickness, the color, the curve, refractive index, because remember, just like fibers, light is going to bend as it goes through glass, and different glass will have different refractive indexes that can be measured with a number. One way to measure the because we talked about how it's a number, but we didn't really talk about how it's measured. There is some advanced instrumentation to measure the refractive index. Excuse me. But one classic way to do it, and you'll see this in some trace evidence examiner laboratories or criminalistics labs. We have a set in our lab in UBOB. It's a set of refractive index oils. And it's just a bunch of little bottles of oil about the size of nail polish, I guess. And it has a number on it, like 1.410. And then there's one next to it that has 1.415. And then there's one next to us, 1.412. So it sort of goes up in increments of 0.005 or something like that. But the oil that is inside those bottles, that number is the refractive index value of that oil. Now what you can do is if you put a piece of glass in an oil with the same refractive index, okay, or very similar, it ends up where the glass almost disappears. And this Becky line, okay, this outside halo and dark line there, disappears. And you may have experienced this where sometimes if you have a piece of glass in a liquid, you can barely see it, and other times it's very clear that it's there and you can see the edges. It's not necessarily how rough the edges are, but it has to do with the refractive index of the glass compared to the liquid that it's in. Okay, so what you can do is you can put if you put a piece of glass in a refractive index of 1.410, and you see a very thick relief line, a high relief or a thick outside line, like this halo and thick black line is very thick, then you know, oh man, the refractive index isn't close to 1.410. I'm going to try 1.610 or something like that. Okay, and it sort of becomes like the clock game on Price is Right, and since this lecture is running long, I'll spare you with my detailed lecture of how to win the clock game, but you can stop by my office and ask me. If you're going to go on Price is Right, okay, don't just go in there blind. Stop by Dr. Linville's office. I watched it when I was in kindergarten. Get some tips. Plinko, I'll give you actually I have no tips for Plinko, but the clock game, I can tell you how to win the clock game. Anyhow, good forensic scientists is sort of like the clock game, where they can look at the thickness of the line and look at the direction, whether the relief is higher or lower, and they can actually, like guess the refractive index in 3 oils. They'll say, oh, I need to go up a lot, I need to go down a little, and they'll be able to get it very quickly. Sort of a skill that some people have. A dyeing's replaced by automated robots. Okay, paint. Okay, let's keep this up, Dr. Linville. What is paint? What crimes are? Paint is a colored chemical coating. It covers cars and houses. Okay, that's not very helpful. How I want you to think about paint is it's obviously a liquid, but think of it as being composed of 3 categories of things, or 3 things. The vehicle is the main component of the paint. So it can be it can be an oil-based vehicle. It can be an acrylic or water-based vehicle, I guess. And don't be confused. A vehicle doesn't mean car here. It means like sort of the main component of paint. Okay, the carrier of everything that's in the paint. And then you have your pigments. So the pigments give the paint the color, and if you've ever had paint mix, you know that you start out with a white paint, and then it just squirts, different combinations of the color in it, and you can, match it to your favorite stuffed animal or some other weird thing. And then extenders are different chemicals in the paint that affects things like its gloss, texture, opacity. Okay, so eggshell paint are going to have different extenders in it than a super gloss paint. So these are sort of the 3 categories of items that can go into paint. So when you're analyzing paint, you sort of try to determine what pigments are in there and what levels are the pigments. You can also just look at the overall color. And then also sort of the glossiness, or you may be able to do some chemical testing to find out what materials are in there to give it its different texture, gloss, etc., etc. And then finally, it's pretty simple analysis to do to find out whether it's oil-based or acrylic-based or some other tempera base, is that a type of paint? I don't know. Okay. How is paint involved in crimes? It used to be involved in hit and runs, and I did not have much success in finding a hit and run. But a hit and run, we actually have had a couple recently that have been on the news, where it's somebody, whether it's a person walking, a person riding a bicycle. I have to say, just if anybody is thinking about walking across 280, just don't try to find another way. I don't know, hitchhike or something like that. Since I've lived here, there have been numerous, it has to be at least once a year, where somebody gets killed by a car trying to walk across 280. You know, they need to put a walking bridge or something. Anyhow, so hit and run is if somebody hits a person or a bike or another car and then just drives away from the scene. When the car strikes that item, okay, paint may be chipped off of the car and left on the victim or left at the crime scene. Now, this used to be very popular when cars were painted, and Earl Shive would paint your car for $99.95 or whatever. Now, a lot of cars don't really have paint on them. It's more like sort of a colored plastic that the car is composed of. But it's still where anytime you have paint that is chipped off of one item, be it a car or a house, you know, during a burglary, and is transferred from a person or place, or excuse me, from a thing to a person or place, then you can analyze that paint chip and you can compare it to the paint of the item you think it came from. You'd collect it just like everything else, hand, forceps, maybe a tape lift, seal it in a plastic container. And paint has one, you know, of all the things that we're talking about, both glass and paint, you can actually do what's called a fracture match. And this would be like an individual characteristic. If you find a chip of paint and it fits like a puzzle piece perfectly in, you know, back into the location from which it came, then you may be able to go into court and say, yeah, this paint chip definitely came from this location. Excuse me. But in general, when paint is analyzed, it's just like all the other trace evidence we've talked about. You try to collect as many class characteristics as you can, color, chemical composition, the presence of any pigments or extenders, and then you just try to comment on the rarity of that. You know, well, this paint that we found on the victim matches the paint of this car, but there are a lot of other cars that have this paint as well. Okay, and then leave it to the attorneys to bring up facts about, you know, like there's, you know, scuffs and chips on the car. It was seen driving away with an identification of a license plate, et cetera, et cetera. And for paint analysis, just like fibers, this infrared FTIR or IR, these spectra where you can tell the chemical composition, that comes in very handy. Also, paint can be found in multiple layers. So if you do have a paint chip that is not just white paint, but it looks like it's white paint over blue paint, which is over red paint, obviously the more layers you get, the more unique that paint is, the more unique the source is. All right, soil, which I think this is finally our last thing here. And this is, I mean, we mentioned like 4 different things when it comes to trace analysis. This can be numerous. It can be lipstick. It can be some other type of makeup. It can be, I'm trying to look around the room, like finding other things that could be trace evidence, like a piece of jewelry, like a link from a piece of jewelry. It can be so many things, but the trend hopefully you see is the same, where you just try to identify class characteristics, compare them, and see if they match. Now, soil is a little bit challenging because it's a mixture of a lot of different things. Animal, vegetable materials, minerals are in soil. If you look at soil underneath a microscope, you'll find that it's, you know, has a lot of different, it's composed of a mixture of a lot of different materials. But where soil is difficult from a forensic science perspective is, remember, all of these pieces of evidence when it comes to physical analysis, it helps if the evidence doesn't change over time. In other words, if I'm analyzing soil from the suspect's shoe, okay, then, and I think it came from my yard, then I want to make sure the soil in my yard is the same today as it is next week, as it is in the winter, as it is next spring. And in some cases, that's not necessarily true. But for the most part, soil in a specific location doesn't change that much over time. Also, I want to make sure that soil is unique to a given area. This is where soil analysis becomes very difficult because the soil in my yard is probably similar to the soil in my neighbor's yard, probably similar to the soil in our neighborhood, and then it's sort of like how big does the neighborhood have to go? And I'm sure you can probably find soil from a yard in Vestavia Hills that's similar to soil in a yard in Chelsea. Okay, maybe the soil doesn't change that much over that time. So it's where you have to analyze it and become a soil expert. You need to say, okay, how rare is this soil? Where would this type of soil be found? And since there's not a lot of soil evidence and there's not a lot of soil databases, that type of analysis can be a little bit difficult. Hey, maybe it's a fun pet project to work on. And you know, surveyors and people who look at land, do surveys, and test soil are probably in a better position to do this type of analysis than some forensic scientist that doesn't do it as often. Okay, so it's possible where you could get dirt off of a suspect's shoe, you know, if it's really muddy and you're trying to trace it to the site of a shallow grave, do some analysis and see if the evidence matches. Okay, since soil, sometimes we're dealing with larger samples. Maybe an envelope, a small plastic envelope won't cut it. Maybe you need a jar or a vial, especially when collecting your known samples from the scene. You look at all the materials, you try to identify them, you try to semi-quantitate them. You know, is there a lot of quartz stones or is there a little bit? Is it high in sand, low in sand, high in manure, low in manure, stuff like that. And then just make the comparisons. And again, like I mentioned, it relies on soil being consistent over time in one location and different in different locations. Both of those things are sort of true with soil, but can be difficult to be very knowledgeable about and to testify specifics. Okay, that's it for the lecture on trace evidence. So hopefully the common themes in these 4 types of trace evidence you guys would be able to apply in other types of trace evidence. It's helpful to an investigation, but the best that you're going to get from the lab is a maybe answer. You know, everything's consistent, so maybe these fibers found on the dead body came from the suspect's car. You're not going to get a definite answer, but it can definitely help with an investigation, help with the case, and help with the prosecution. Okay, the trick is for the forensic scientists to be sure to relay all of the information they have to the jury and then also be ethical and discuss the limitations. In other words, what other cars also have those fibers, you know, what other boats also have that boat glass in them, et cetera, et cetera. Okay, we'll stop here. Annette, I have you down for attendance. You can jump out of the room at any time. If you do have any questions, feel free to throw them in the chat box. I think last week Garrison had a good question that I answered in the recording, so the class can benefit from it. For everybody else, let me know if you're having any troubles with the course. I'm trying to look at grades this week from the first assignment and the first 2 quizzes and send out any early alerts to sort of give you a little tap if you've missed a quiz or assignment and need to make it up, or if you're having trouble, giving you some tips on how to do a little bit better in the course. All right. Most important thing is keep listening to these lectures. Carve out time each week to do the work. Try not to just show up on Monday and type out a quick answer to an assignment, or show up on Monday and do your best on a quiz or exam. Try to prepare for it just like an on-campus course. And everything's crammed tight. It will be August before we know it. All right. That's it.